Hi guys, I want to try to go through these periodic trends slides as fast as possible so that way this video can be as short as possible for you. So today we talked about in class, we focused mostly on atomic radii, which we didn't get a lot to, but at least we started to talk about it in every class. We also mentioned that there were 3 factors that influence a periodic trend. So we are specifically focusing on 3 different types of trends. We want to focus on atomic radii, we want to focus on ionization energy, and we're also going to focus on electronegativity. So the first one we're going to talk about is atomic radii. But before we talk about it, we need to understand what the factors are that can influence all 3 of those types of trends. So one factor that we talked about today was energy levels. So if you're looking, guys, on slide number 5 on the ones that I posted on the blog, that says periodic table trends influenced by 3 factors. The first one is energy levels. And all energy levels mean is that as I keep moving down different rows, I add more and more energy levels. So if we think about this in terms of atomic radii, I know that as I add energy levels, the size of the atom is going to get bigger and bigger and bigger. And it's because I keep increasing the amount of energy levels, okay? Now, the second factor that can influence a periodic trend is called nuclear charge, or I wrote on your PowerPoint slides, charge on the nucleus. Now, I think we started to talk about this in all of the classes, but I don't know that we really got all the way through it. So nuclear charge is your second thing, and nuclear charge, next to the side of that on your slides, I put numbers of protons, and that's really important that you understand that it's really the protons that are doing all of the work here. It's really the nucleus that's doing the work, but specifically the protons. Now, an energy level, let's go back to that really quick. An energy level can influence a column or a family, but an energy level is never going to influence a row or a period, because if I go across the row or I go across the period, it's going to try to stay the same. So energy level, just remember, will only affect columns or groups or families. Nuclear charge will only affect a row or a horizontal period. Now, nuclear charge. If we compare, let's compare two different elements. So if you're looking at your periodic table, I want you to look on the second energy level, which would mean the second row, and let's look at lithium and then compare it to fluorine. Now, lithium, I know, has 3 protons because it tells me the atomic number is 3, so it tells me 3 protons. I also know that if it's neutral, it's going to have 3 electrons. Now, that one electron that's on that outermost ring, this one electron that's on the outermost ring doesn't necessarily want to stay there, because think about Bohr's model. To fill this outer shell, it would need to gain 7. Or it could lose this 1 and then just be left with this 2 here on that shell. So lithium doesn't have, its nucleus doesn't have a strong hold on that one outer electron because it wants to give it away. So it really doesn't matter how closely or how tightly the nucleus will hold on to those electrons. Now, as you move across that row on the periodic table, you only have 2 rings because you're still in the second row. So it doesn't matter which element you choose, you still only have 2 rings, or you still only have the 2 shells around the nucleus. So the distance is the same. So I can't really think about nuclear charge in terms of distance. But let's look at fluorine, for example. Fluorine has an atomic number of 9, so that means it has 9 electrons. So it's going to have 2 on the first ring, and then it's going to have 7 on the outer ring. Something like this. So it needs 1 more. It doesn't want to let go of those electrons at all. Why? because it only needs one. So it's going to take a lot more energy to pull all 7 of those electrons off than it would be to just gain 1 extra electron. Which one has more protons, lithium or fluorine? It's a really easy question. Fluorine has more protons. But look at their shells. I have 2 rings here, I have 2 rings here. So because they're the same amount of energy level, really what's causing these electrons to be pulled in more tightly to the nucleus is the number of protons that are there. So think about noble gases. For example, neon. Neon has 8 valence electrons on that outermost ring, on that second ring, because it's in the second row. It will not give those electrons up for anything. It will hold them as tightly as possible. It's like hugging them, it's squeezing them so tightly because it's unreactive, it's stable. So because it's stable, though that nucleus wants to pull in those electrons really tightly, which is why atomic radii, the trend decreases as you go across, as you move from left to right. So I'm starting with lithium, which is fairly big. It's a fairly big atom, and it's a bigger atom because that 1 electron doesn't really have as much pull between the nucleus and that electron. So it doesn't really care so much, it's not hugging it in so tightly, it wants to give it away. Now, as I move across though, as we move to the nonmetals, we know that those need electrons, or they want to gain electrons, so they're going to hold on to their electrons more tightly. So like nitrogen, it's easier for nitrogen to gain 3 electrons than it is to give 5 away. So it's going to pull those 5 electrons in a little closely. Oxygen has 6 valence electrons, so it's going to pull those valence electrons in even tighter than nitrogen would because it only needs 2 electrons to be stable. Fluorine has 7 valence electrons, so it's going to pull in those electrons even more tightly than oxygen would because it only needs 1 electron. And neon has them all, so it will not give any of them up. So nuclear charge is all about the nucleus pulling in the electrons tightly, or as tightly as it possibly can. And it's all based on, guys, this kind of like force between protons and electrons, and this like electrostatic force. So the nucleus can pull in electrons more closely. So that's what nuclear charge would be. Now, the other example, or the other factor that influences periodic trends is a shield. It's called shielding, or the shielding effect. Now, on the next slide, I tried to talk about what shielding was. So this is slide number 6. For shielding, this is where the outermost electrons, we can think like the valence electrons, their view is blocked of the nucleus. So because of that, they may not have as strong of an attraction to the nucleus as an electron that would be closer. So let me give you an example. Okay. Guys, let's assume, work with me here. Okay, let's assume that my Starbucks cup is the nucleus. This is the first electron closest to the nucleus. That's chocolate. Then I have another electron, vanilla, and then I have my third outermost electron here would be nutmeg. Okay, so this electron is really close to my nucleus, so the attraction is pretty great. But this electron, vanilla, is shielded by chocolate, so it may not have the best attraction because this chocolate is in its way. So I can't really get to it. It can't see the cup or the nucleus as best as it possibly could. If I look at nutmeg here, it's shielded even more, not only from vanilla, but it's also shielded by chocolate. So because this one, nutmeg, is shielded by those two, the attraction is weaker to that nucleus, not only because it's far away, but also because these two, 1, 2, are blocking its view. So that's what shielding means. Okay, let me set this back up for a second, guys. Give me 1 minute. Okay, so that's what shielding means. It means that we can block kind of an electron's view, or other electrons can block views of electrons that are really far out. Okay, now we're gonna model this tomorrow in class, but just so that way you kind of have a better understanding of what shielding would be. Now, shielding does nothing with a period or with a row. The only thing that shielding will affect is a column or a family. So if I look at these two, lithium and fluorine are in the same row. So this electron can't shield this one because they're just moving around on that same orbit, right? If I'm thinking about it in terms of Bohr's model. So because of that, shielding can't affect a period, because this electron will never block this one, and that one could never block that one, and that one could never block that one, because they're moving on that same ring. But this electron could block this one, so it depends on group. So shielding will only affect a group. It will only affect a column. It will not affect a period, or it will not affect a row. Okay, guys, so those are our 3 factors that can influence periodic trends. Now, to move on with this, let's talk about those 3 different trends that I want to focus on. First one was atomic radii. We started talking about that today. All I care is that you understand that atomic radii really means like the size of the atom. And we found the size of the atom by taking 2 elements of the same kind. So let's assume like a hydrogen and a hydrogen, and we bonded them together. And once we bonded them together, we found the distance between the 2 nuclei. So I found the distance from this nuclei to that nuclei, and I divided that distance by 2. Because then we could assume that, for the most part, that has to be roughly the distance of one of those hydrogen atoms, okay? Now, as we go across from left to right, across the periodic table, so for example, if I'm moving from like lithium to neon, the trend for atomic radii, meaning that as we move from left to right, as we move across a row, atomic radii will decrease. So the size of the atom decreases. And think about why. Nuclear charge is the only thing that can affect this, meaning that the electrons are holding on to, or the nucleus is holding on to that electron or those groups of electrons with all of their might. So it becomes smaller and smaller and smaller. The nucleus is pulling the electrons in. As I think about atomic radii going down a column or down a family, they get bigger. And it gets bigger because I add energy levels, and shielding also has a little bit to do with that, because the 3rd energy level, if I have 3 rings around my Bohr's model, would be shielded from the electrons that are in the 2nd and the 1st. And so I don't have as much of an attraction between those electrons and the nucleus, so the space can be a little bigger. If I add a 4th energy level, I'd have even more shielding. So shielding and energy levels can kind of play together in terms of a column or a group. Okay, so guys, those were the atomic radii trends. So I will ask, what's the atomic radii group trend? And you would say, as atomic radii, as we go down a column, atomic radii increases. We know they get bigger. Why does that happen? Because we add energy levels and because they're shielding. If I were to ask you, what's the trend of atomic radii as you go across a row? And you would say atomic radii decreases because of nuclear charge, because the nucleus is pulling those electrons in even more tightly because it doesn't want to let them go, okay? Now, on your slides, I think, guys, this is slide number 9, and we just talked about this. Energy levels and shielding have an effect on the group, and nuclear charge only has an effect on a period or on a row. So we already talked about that. Now, okay, slide number 10. So on slide number 10, there's something that's called an isoelectronic ion. Iso meaning equal, and electronic meaning like numbers of electrons. So equal amount of electrons. That's what this is meaning. So I gave you